Hello, and a very warm welcome to the presentation about Evonik's latest development in the field of our particle technology. My name is Markus Vogel, Head of Applied Research and Technology of Architectural Coatings in the Evonik business line of coating additives. Today I want to present to you the new particle technology called SPHERILEX. Many of you already know the well-known fumed silicas, the aerosol as rheological additive, the ACE mat, the matting agent, the precipitated silicas for matting of coatings, or the Tego nanoresins, which are nanosized particles in a liquid medium. The new technology now is called SPHERILEX. Here we are talking about very spherical particles based on precipitated silicas. So the same processing as the matting agents, in contrast to the fumed silicas, for example, the aerosols. The new technology now shows you the very spherical particles with very beneficial properties in your coating formulation. On this slide, we see the production process of the new SPHERILEX technology. It is a precipitated process, means it is a wet chemical process where we form primary particles of SiO2 first, and then the primary particles resulting in interparticle siloxane bonds, and at the end we have aggregation of particles. After drying, we really have spherical shaped precipitated silica particles. When we compare the both processes, so on one hand, the conventional precipitated silicas, for example, our matting agents called ACE mat, and on the other hand, the new technology SPHERILEX, there are big differences. Those are precipitated silicas, but the SPHERILEX are produced in a continuous process, which is highly controlled. In contrast to that, conventional precipitated silicas are produced in a batch process. After the precipitation step, we wash the formed silica particles. Here the difference is that in the SPHERILEX process, we need a relatively low water content to wash out the salts. After washing out the salts, there is a process step with spray drying. And here, in contrast to the conventional process, we need much lower energy to dry the particles. The last step is a milling step, which is for the conventional precipitated silicas the essential step to create a certain particle size. So this is a critical process in the conventional process. Here, with the SPHERILEX particles, we have just a light milling only to ensure the particle separation. This ends up in completely different bulk densities. As you see on the right-hand side, that the bulk density of the conventional precipitated silicas is much lower than the bulk density of the SPHERILEX technology. The final product of the SPHERILEX flows like water. Here we see some microscope pictures of the final product, the SPHERILEX particles. And you see the very spherical shape of the particles, which we form in the reactor and which leads to a uniform distribution. The average particle size can be adjusted between 3 and 20 microns at the moment. Other parameters controlled by rate, temperature, and the concentration of the raw materials. Very unique is the particle size distribution. So with the SPHERILEX, we have a very narrow particle size distribution at the end. And this is completely in contrast to other materials which are used for the same effect, like ceramic particles. They mostly showed a broader range of particle size distribution. So at the end, a narrow particle size distribution can lead to more benefits in your formulation. In general, you can say the small particles, they cannot change your properties in the coating, or you cannot achieve the required properties. The big particles, on the other hand, they can cause big trouble in your formulation. For example, when we look at the rheology, they can make trouble, or when we go in the direction of glossy coatings, they can influence the gloss in a negative way, or other properties can be influenced negative by coarser particles. What do we want to achieve by using the SPHERILEX particles? We want to create a micro-rough surface. So spherical particles produce a rounded and more physically robust surface profile that resists burnishing and abrasion. With these spherical particles, you can achieve that in a very good way. So at the end, you have less contact areas with round particles on the surface, where you see on the bottom pictures that when you use irregular shaped particles, that the surface is not very regular. On this slide, we see some microscope pictures with different magnifications. On the top line, you see pictures with a magnification of 250, and on the bottom line, a magnification of 500 times. On the left side, we see the control paint. This is a typical dried interior wall paint with an irregular surface, roughness, irregular shaped particles on the surface. We took this formulation and replaced some of the common fillers, for example, calcium carbonate, by SPHERILEX. And this you see in the second and in the third picture on the more right-hand side. And here we see with smaller particles, the DP111, and with bigger particles, the DP112, really the spherical particles on the surface. So we have a very regular surface created by spherical particles. First reason or first benefit of using these spherical particles is to improve the burnish resistance. So first of all, what is burnish resistance? Burnish resistance is a coating's ability to maintain its visual appearance after being rubbed by soft types of objects like leather, sponges, cloth, or human hands. So after treating the surface, you see gloss differences, which is very visible on the picture on the right side. There are many different test methods in the market to test the burnish resistance of interior wall paints. On one hand, there's an ASTM method, which uses cheesecloth to rub over the surface. There is another test method from MPI, the standard 44, which uses synthetic leather. From CRGI, you find different test methods, a wet method and a dry method. CRGI stands for Coating Research Group. And we have also developed some internal test methods in Evonik. In all of these test methods, it is more or less the same procedure. You treat the surface with a soft device, and then you measure the gloss difference before and after treatment of the surface. So SPHERILEX, impact on rheology and binder efficiency. The amount of external phase required to surround the particles is based on the natural packing arrangement and the absorption within the particles. Usually you try to reach a high packing of your formulation. And this is even more easy when you use a very narrow particle size distribution. You see also that the particle shape influences the packing of your formulation. On the left side, you see just round spherical particles. On the right side, you see irregular shaped particles. And in the middle picture, you see different particle sizes. Here, the red spherical particles express the SPHERILEX particles. And here you can achieve a very high packing of your formulation. This narrow particle size distribution and the surface design creates flexibility for low oil absorption, low binder demand, excellent flow properties, and the opportunities to manage particle packing effects due to controlled particle distribution. Coming to some results. When using solid particles, they will always influence the rheology of your coating, the viscosity at the end. On the left side in the graph, we see a standard paint with a viscosity at different shear rates. When we now replace some of the calcium carbonate by SPHERILEX, you don't see a big increase the other way around. In some cases, you see a decreasement of the viscosity. So you have no negative influence on the viscosity at all when you replace, for example, calcium carbonate by the silica particles SPHERILEX. In this case, we tested a paint with a pigment volume concentration of 45% based on a styrene acrylic binder Acronal S790, which is a very typical binder in the market. The coating properties are really improved by using SPHERILEX. What you see here in the graph is, on one hand, the burnish resistance, and on the other hand, the wet scrub resistance of an interior wall paint. We tested here two different paints. One, the deep purple bars express a waterborne acrylic paint with a pigment volume concentration of 40%. The gray bars express a waterborne emulsion paint with a pigment volume concentration of 55% based on a VAE emulsion. You see that the burnish resistance is decreased, means is improved. Burnish resistance here is expressed by the delta in the change of gloss at 85 degrees. And you see that we could decrease the delta from 1.3, respectively 1, to 0.8, respectively 0.6 in the other formulation, which is much better than, for example, in comparison to ceramic particles. On the other hand, we tested the wet scrub resistance according to the ASTM test method D2486, means we scrub over the surface until the substrate is visible. The control paint showed nearly 1,400 cycles until you see the substrate shining through the coating. By using the spherical particles, in this case the great SPHERILEX DP115, we could increase the cycles from 1,400 to approx 2,000 cycles. So a very big jump in the wet scrub resistance. Very good improvement. In another formulation, in this case, pigment volume concentration 40% based on an acrylic, pure acrylic emulsion, we tested again the burnish resistance. Again, the delta, the change in gloss at 85 degrees. On the right side, you see the bars of the control just with carbonate fillers, calcium carbonate fillers. And then you see the reduction in the gloss change with SPHERILEX DP115. In this case, we could reduce the change, so the delta in the gloss, from nearly 3 gloss units down to 0.2, 0.3 gloss units, which was very visible after the treatment on the surface. So in this case, SPHERILEX DP115 could really improve the burnish resistance of this emulsion paint. And this we tested also at different layer thicknesses, wet layer thicknesses of 75 to 250 microns. So particle orientation and burnish resistance correlate with each other by using these particles. On the left-hand side picture, you see that the spheres can settle down into the arrangement of the surrounding pigments, so they are not really visible at the surface and cannot act at the surface. For improving the burnish resistance and the wet scrub resistance, it is very necessary that the spherical particles appear at the surface. If it is like on the left sides, then the spheres are more mobile than other particle shapes within the wet film, and the burnishing can damage the surrounding pigments which are on the surface. Larger spheres are more likely to remain above the surface, where they can protect the film from burnishing, which you see in the middle picture. So particle size limits how deeply they can settle in among the other pigments. The spheres, in this case, protect the pigments from burnish damage. On the right-hand side, you see smaller particles, smaller spherical particles. And here, the rheology or surface treatments can help to preserve SPHERILEX particle orientation at the surface, where you need them to improve the burnish resistance. So even small particles, small spheres, protect the pigments from burnish damage. Coming to our product portfolio of the new SPHERILEX technology. Currently we have 3 products in our portfolio, from DP111 to DP115. The 3 products vary mostly in the particle size. You see, everything is based on silicon dioxide. All the particles are spherical, but the D50 value varies. It is easy to remind, the higher the number, the bigger is the D50 particle size in micrometers. When talking about DP111, we have a D50 value of around 5.5 microns. Going up to the DP115, we achieved a particle size, a D50 particle size of 15 microns. All the other parameters are similar to each other for all the products. But in general, you see that we have a very low BET surface area with around 6 square meters per gram and a very low oil absorption number with around 45 grams per 100 gram, which is very low for a filler particle and which is similar to common fillers, not similar to other silica particles like fumed silica or matting agents. These particles have usually a much higher oil absorption number. The specific gravity of the SPHERILEX particles is similar to other silicon dioxide particles with 2 grams per cubic centimeters. To summarize this technology, SPHERILEX product properties is they have a very high sphericity. We can achieve a very narrow particle size distribution. The particles showed a very low binder demand or very low oil absorption number, and therefore they have a very low viscosity build in your formulation. For your coating, this means you can improve the burnish resistance as well as the scuff resistance. We saw that you can also improve the wet scrub resistance, which is very important for architectural coatings. Abrasion resistances could be improved, and due to the very special shape of the particles, so the sphericity of the particles, you can also achieve soft touch properties on the surface. This was already the end of the presentation. Hoping this information aroused interest for the development and improvement of your coating formulations. In case of any questions, or if you need more information about this technology, feel free to get in contact with us by phone or by email. Thank you very much for your attention and talk to you soon. Goodbye.